Thanks for coming. The next talk will be about AI. I think you all have heard of AI. But when you think of AI, maybe you think about a data center with multiple GPUs and all of this to manage the AI. But here we have a talk where we will learn that we can do AI in the browser. Please welcome Jason Mays.
Hello, everyone. Thank you for coming to my talk. I'm Jason Mays. I'm the Web AI lead at Google. And of course, today we're going to be learning about what's new with web-based machine learning in the browser in 2023. So before I get started, I just want to shout out that, of course, machine learning could influence every industry out there if it's not already doing so right now. And now is a great time to learn about how to do this in JavaScript as well as Python. Now, I'm sure many of you have heard one of these three terms: artificial intelligence, machine learning, deep learning. In fact, put your hands up if you've heard one of those terms being mentioned at some point. Now, keep your hands up if you can tell me the difference between those three terms. Oh, all the hands are going down. You're in the right talk. This is great. So I want to make sure we all appreciate what AI, ML, and deep learning actually is before I give you the updates in this space. So artificial intelligence, or AI for short, is the science of making things smart, or more formally, human intelligence exhibited by machines. And this is a very broad term, and right now, we're actually in the realm of narrow AI. All this means is that we can create systems that do one or many things as well or better than our human expert counterparts can do, such as object recognition. And a good example of object recognition could be scanning brain tumors and finding these abnormalities in those brain tumor scans. And we can do that really fast now, as good as a doctor. Now, machine learning on the other side, or ML for short, is at the implementation level. This is the program that you can create to learn to find patterns in the data that you present to it. And the key thing about these systems is that they can be reused. So if I create a system that can recognize cats, I can use the same code to then recognize dogs just by giving different training data to that system. And that's a really important point, using the same code. And this is very different to how we used to program in the old days. So if we're trying to make a spam classification system, for example, in the old days, you might use conditional statements, like if an email contains a certain word, mark it as spam. If it contains another word, mark it as spam, and so on and so forth. Now, this is not very good because obviously, the spammer can get wise to what words you've got on your list and just change the word slightly and get around your filter, which is a waste of your time trying to maintain that list of words. Fast forward to today, and now we use machine learning to do this for us automatically. Every day, tens of thousands of you mark emails as spam, and we can use mathematics and statistics to find what combinations of words appear in those emails in certain forms to then automatically mark those emails as spam for you. So we're in a very exciting time, and there's many common use cases for machine learning out there today. One of them could be object recognition, as I just spoke about. This is an example I actually made in JavaScript in just a couple of hours that allows me to monitor if my dog has been a naughty boy and has gone near the treat. And you can see here that these two bounding boxes have intersected. So if you can recognize where something is in an image and add some custom logic to say when these two things intersect, you could then send yourself a text alert very simply. There's also this scary-sounding thing called linear regression. All this really means is that for some input number, you're predicting some output number. So if you've got a house in San Francisco that's 1,000 square feet, with enough data points, you could predict that might be $1.2 million to buy in the US. And you just basically got this line of best fit going through that data, so you can predict that. We've also got natural language processing. Now, I'm sure many of you have heard of large language models. This is the precursor to that. So before large language models were there, we had natural language processing. And you can see here, I made a Chrome extension that actually understands what you're actually typing. So I ask it, what are the best stargazing days? And it scrolls down to the correct part of the website that answers that question, even though the answer does not contain the word stargazing. So it really understands the context of the language that you're actually asking. And that's much more powerful than just Control F for some keywords. We've also got audio, both in terms of audio recognition. If any of you have got Android smartphones, you'll notice that our speech recognition is good even in noisy environments. And we've also got generative audio, such as this example, which you can try out on that website there, which allows me to convert my voice into a musical instrument. So I can just hum a tune into my microphone in the web browser with no server required, and it will convert my voice to be a flute or a saxophone or something like this in the same tone. So now even someone like me who's not very creative on the musical side has a chance of creating music, which is a lot of fun. And of course, I'm sure you've heard of generative AI these days as well for images. So if you haven't, you can now type a prompt like a photo of a corgi dog riding a bike in Times Square. It's wearing sunglasses and has a beach hat. And sure enough, a couple of seconds later, you get a photo that is exactly that. And the important thing to note here is this has been dreamt up by the machine learning program. So if I asked all of you right now to imagine a purple cat, you've never seen one, but you could imagine one, right? And in the same way, the machine learning is basing its knowledge of cats in the world. It will dream up a purple cat if I asked it to, even though it's never seen one before as well. So it can do all these interesting things too. So in some ways, it's kind of creative too. Now, deep learning, or DL, on the other side of things, is a technique for implementing the machine learning program that we just spoke about on the previous slide. This is one of the algorithms you can use to actually implement the learning to actually happen. And one popular technique is deep neural networks, also known as DNNs. And essentially, these are code structures that are trying to mimic how we believe the human brain to work and are arranged in layers that build upon each other. Essentially, they're learning patterns of patterns. Now, what do I mean by patterns of patterns? Well, imagine in that first layer on the left-hand side, it starts to look for simple things like lines in the image, okay? Very simple things, edge detection, that kind of stuff. You go one level deeper, and those lines might start to combine so that you can recognize simple shapes. You can start to see circles forming, or triangles forming, or ovals forming, as you can see here. You go one level deeper still, those shapes will then combine to allow you to recognize objects. Maybe a face is a large circle with two smaller circles inside with certain proportions and ratios that you can then identify a face in the room. And if you go one level deeper, those specific ratios of the sizes of those circles and shapes and triangles and things might allow you to identify an individual face in this room versus everybody's face. Now, this is a very high-level overview, but in principle, that's what it's doing. And the important thing to realize is that in machine learning, we're always dealing with numbers. Now, as humans, we can see on the left-hand side that's probably a face, and some of you who are historians might even know what face that is. But we need to convert those color values into numbers for the machine to actually interpret. So in case of a grayscale image, black would be 0, white would be 255, and all other shades of gray would be some number in between that. So on the right-hand side is what the computer sees. As humans, we cannot see the face in that anymore. Or maybe some of you can, but I can't. And that's the key thing to realize. We're always dealing with numbers in machine learning. So in principle, then, we've got this machine learning model that does some mathematical magic. We feed it in some numbers on the left-hand side and outpop some other numbers on the right-hand side. Now, what do they actually mean? Well, those numbers on the right-hand side are essentially predictions of how confident it is at representing some output value. So if we assign Daisy to the first one and Rose to the second, we can see that 0.78 is higher than 0.22. Therefore, in this situation, this machine learning model thought, based on those numbers that were given to it, it thinks it represents a Rose, okay? So that's basically how we interpret machine learning models' inputs and outputs. So in summary here, we've got the deep learning algorithm that drives the machine learning implementation, the program you're writing, which then we can add some other logic to give you this grand illusion of artificial intelligence, which we're striving towards longer into the future. And these concepts actually go back to the 1950s. This is not anything particularly new, but it's only now that we've got the processing power at cheap enough costs, all those GPUs in the cloud and processors and RAM and all this kind of stuff is now available at scale, which we never had before. And that's why we've seen an explosive growth over the last 10 or so years especially. So the next logical question then is, how do we train these systems? So for the purpose of this, just pretend you're all farmers and you've got a bunch of apples and oranges mixed in your cart, and you're trying to separate them, okay? The first thing you need to do is identify some features or attributes, if you will. These are things that you could measure digitally with some sensor, so weight with some digital weighing scales and color using a regular camera. And you can then measure those properties for a whole bunch of apples and oranges. Now, going back to your high school mathematics, if you plotted those values on a graph of weight versus color, you might get something like this. You can see the green apples are in the green spectrum, the red are in the red spectrum, and the oranges are slightly higher up in the weight because they're a bit more juicy, they've got more water in them, so they're higher on average. So, if you can draw a line that separates the oranges from the apples, if you find a new piece of fruit, you can then weigh it, measure its color, plot it on the graph, and if it's above the line, it's probably an orange. If it's below the line, it's probably an apple, okay? So if you can get a machine to figure out the equation of that line for you, then you've got yourself a machine learning system, which is capable of separating data so that it can predict new things in the future. And at its essence, that's what machine learning is doing behind the scenes. Now, if that was all it was, of course, I could finish this talk and we'd all be millionaires. But there's a bit more to it. So what if you choose bad features and attributes? Now, if you chose ripeness and number of seeds to classify these fruits, you might get a scatter plot like this. And there's no easy way to separate this data with a straight line or even a curved line for that matter. Now, you might be, well, Jason, why would you choose ripeness and number of seeds for fruits? That's very silly. And yes, of course, in this trivial example, it's obvious that would be a bad choice. But what about those brain tumors we spoke about earlier? What would you use as features for those from image data? It gets much harder with more abstract things. So in order to separate these data points, we could then introduce a third dimension, maybe. So maybe we have weight added back in, and now, instead of using a line to separate the data, we can use this rectangle in 3D space, and behind this rectangle, we've got the oranges, and in front of this rectangle, we've got the apples, okay? Now, it turns out that 3D is not enough in machine learning. You're typically using 10D, 100D, 1,000 dimensions, even millions in the case of images. And as humans, you cannot visualize that. I've tried and failed miserably. But basically, you just can't do it. But the maths works out the same. And the mathematical name for this rectangle in 3D space is called a plane, okay? And when you're using high dimensions, you're using a hyperplane to separate data in high-dimensional space. So a hyperplane is just one dimension less than the number of dimensions you're trying to classify, and then you're able to separate that data in much the same way we're doing here in the 3D, okay? So with that, there's two kind of problems you're trying to solve in machine learning, especially when you're starting out. You've got classification problems. Is it a cat? Is it a dog? That kind of stuff. And you've got regression problems. For some input number, predict some output number across some continuous range of values. So it should be easy, right? We've got dogs, we've got mops. Very different. We should be able to feature engineer some features that can separate mops from dogs. Except some dogs look like mops. And even I, as a human, struggle to distinguish these. And my reason for showing you this is that it's really easy to introduce bias into your machine learning model. You might think you've got all the training data in the world, but you probably don't. And this is very apparent in more realistic examples, like maybe speech recognition. Maybe I'm over in England trying to make something that recognizes English-speaking people over there, and I go around the whole country, sampling all the people, getting examples of people speaking into the microphone, and it works 99% of the time. It's like, great, I'm going to launch. And then I come over to France and try it out, and of course, with the accents over here, it fails miserably for some reason. And it wasn't because I was trying to do that on purpose, but I've got a bias in my system where I didn't have enough training data to represent all the people that could use my system. And it's actually very easy to do that accidentally if you don't think about it in advance. So please be aware of that when you're making ML systems, and always think about who your users might be, even if they're not your immediate set of users. It could grow one day to be more people. So that brings me, of course, to machine learning in JavaScript, which is a very exciting topic that I'm very passionate about. So TensorFlow.js is a machine learning library for JavaScript developers. It's just like the Python version you may have heard of, but written in JavaScript. So that means we can run anywhere that JavaScript can run, which is basically everywhere across billions of devices globally. And we can see here that the usage of TensorFlow.js on its own has grown tremendously since 2020, over 20x usage. We're now at 1.2 million monthly downloads and over 300 million cumulative downloads to date. And if you can combine these stats with our other teams at Google, like MediaPipe Web, we actually have crossed 1 billion downloads for the first time. So this is a really exciting time for JS developers to be getting involved in machine learning, because a lot of people already are. Now, many popular Google products are using machine learning in the web to power them. Some of you might have used Google Meet in the past, and you can blur the backgrounds using our segmentation models. And this can save literally hundreds of millions of dollars per year because you're not doing this processing on the server side. So cost is a big factor for this too. And it's not just Google thinking about these things. Just this September, actually, Adobe Photoshop Web was launched, and they're using TensorFlow.js models to bring some of their machine learning smarts to the browser as well, to replicate the functionality they have in their native desktop application, but it runs in the browser. So this smart selection tool now has a really good user experience. Instead of having to send potentially a very large image to the cloud to be segmented and then sent back again, which takes maybe a long time, you can now have it happen almost instantly on your local device using your own resources. And because of that, you have privacy too, because that potentially confidential document is not sent to the cloud to be processed. Also, you could work offline as well. So you could be in the middle of a field and still use Photoshop in this case. So I'm very excited to see where Adobe Photoshop goes with all of this. And this year, I want to also announce we've created a program called Visual Blocks for machine learning, which is a JavaScript framework for developers that enables low or no-code ML authoring within any product ecosystem, including yours. And here you can see how we're able to make a full end-to-end machine learning-powered web app using the available building blocks defined by our team, such as segmenting the body from an image, performing style transfer, or even combining model outputs with real-time shader effects, just by dragging nodes and connecting them together in seconds to create a graph to perform a desired task. Now, the provided example editor shown here allows you to drag outputs and inputs to any nodes they're compatible with, so you can bring ideas to life in a very fast manner and then share it with a team for feedback and iterate and so on. And soon, you'll be able to use this in your own products and services. Now, we've bootstrapped this project with a whole bunch of useful off-the-shelf machine learning models, input nodes for accessing common sensor types like the webcam and microphone, and visual outputs to compare results from the models and use those with ease. And you can use all of those things out of the box. And as you may have guessed, we even interact with third-party APIs too, like in this example, where we're talking to the Google Palm 2 large language model API. And this is really powerful because in this situation, we're actually asking it to generate 3 emails in different tones to solve a problem that we have. So maybe you've got a customer service problem with some retailer that you've just been to, and you want to generate a nice email to send to them to get your money back. And here, we've asked to do that in 3 different tones, maybe a formal tone, a casual tone, and some other type of tone. So we go to the Palm 2 API and say, hey, Mr. LLM, generate us some emails to solve this problem for us, given these contexts. Back come 3 emails. And then we can take those 3 emails and send them back through the Palm 2 API and say, hey, given these emails, which is the best to send and why? So then you get these very powerful systems that allow you to actually make decisions in your daily life to be more efficient or solve a problem that you have. So really incredible stuff. Now, once integrated into your system, however, you can then add custom nodes for your own client-side or server-side models to do whatever you want, allowing you to chain together things that matter to your team in almost any way, and bring your ML-powered ideas to life visually in a manner that everyone can use to launch ideas into production faster. And it's completely themable too, so it can fit your brand and style. Now, if you are more on the server side and use Python, we actually also run on Python collabs as well, so you can expose your code styles as draggable nodes, allowing you to embed an interactive live demo at the top of your collab for everyone to try right there and then, instead of having to go to a separate website. So you can head over to the link shown to try this for yourself later on. I'll also be doing demos upstairs later. And you can use it for a whole bunch of useful tasks across the machine learning space. So I'm going to switch to a live demo. Let's hope this works. Let me go over to here and make this larger. And jolly good, that'll do. So this is Visual Blocks, essentially, when you go there. And I can drag out an input image from the left-hand side here. And you can see we've got a node. Oh, no, we can't see that. OK, well, there's a node there with some properties you can configure. OK, and at the top, there's a visual representation of that node. So this is an image node. It has lots of images in it. OK, now I can change those images to select this guy instead, and I can put any image I like there. Now, when I drag out from this node's edge here, I get a bunch of recommendations of other nodes that have images as inputs. So it's automatically pre-filtered the things I can connect to, which is very useful. Now, I can use this body segmentation model, for example, and place it there. And right now, we're going to download a TensorFlow.js model to run locally in the browser. And when it's ready, I can visualize the results of that. So I can drag out from this on the right-hand side and use the mask visualizer to see what it actually just did. And you can see we've now removed the background from this image in under 15 seconds. Not too bad. But let's solve a real problem. I know all the cool kids in the room probably like their augmented reality filters on Snapchat and Instagram and that kind of stuff. So let's pretend we're trying to make one of those, okay? So we can take this segmented output and pass it through a second TensorFlow.js model. And here we can go to the model section, and we can choose face landmarks, for example. And I place that in there. It's going to download from the cloud the TensorFlow.js model and then run it locally once it's downloaded, so our privacy is preserved. And I can then, again, visualize what has just happened by placing the visualizer node. And now we've got key points on this guy's face that can be recognized, 487 key points to be precise. And all of that happened in just a few, 20 seconds if I wasn't talking so much. So now we can take those landmarks that we just discovered and put it into an AR sticker node that allows us to take 3 inputs. And if you can't read it, I can't read it either, it basically says, we've got the face landmarks as the first input. We've got some sticker image that we want to use. And we want the original image, which is the segmented image that we're taking from the left-hand side. So let's find ourselves a nice sticker image to use. And I think I've got some beautiful love hearts here. Lovely. So let's take those love hearts, just a PNG image from the internet with some transparency. And what I can do now is drag out another input image. Whoops, there we go. Let's place that over here. I can click on the Manage button, and I can go from URL and specify my beautiful love hearts that I want to use in this demo. And we now have some love hearts we can use. So in this output window, I can now select the love hearts. And now this green node at the bottom is pumping out love hearts, OK? So we're now going to connect those love hearts to the oh, no, 1 second. There is a slight bug where I used this demo before. I need to set that to 0, 0, just to be reset from the previous demo. 1 second, sorry, ignore that. This will be fixed by the time you use it. So I now connect this to the sticker image as so, and now the love hearts are in his face, okay? Now we can change the anchor point. In this drop-down, we've got other anchor points, like the face, the eyes, the nose, the mustache. So if I click on nose, you can see it now connects to his nose, okay? So you can start to anchor things to this guy's face, which is pretty cool. And we can also, of course, kind of scale this up and down to make it bigger and smaller in real time, and maybe offset it slightly to the right-hand side, okay? Great. Now, if we're happy with that effect, that's a good starting point, but this is JavaScript. We can work in real time because we're running locally. You don't have any cloud involved. So I can delete the original input image and go to the camera input node instead. And now I can connect this in to where it was before, and hopefully, if I can get it there, you can now see me live on stage, segmented with love hearts around my face. And all of that's possible in a couple of minutes if I wasn't talking so much. So you can actually build some pretty advanced things very fast. So let's continue this. Let's transport myself to a different background now. So let's take this output, which has got a transparent background, and combine it with a second image to transport myself to a nice, beautiful, sunny location. So let's drag out another input image from the left-hand side and put this over here. And again, I can select this nice sunset instead here, and I'm going to connect that to be the second image input over here. Jolly good. Now, what's happened? At the top left here, you can see we've got this output. Whoops, sorry, 1 second. My mouse is a little bit wonky on the trackpad here. There you go. There's the output. Right now, image 2 is on top of image 1, so I need to reverse that around. So what I can do is I can go to the mode and select destination over, which is that one. And now you can see I'm at the beach with love hearts and all that good stuff. But it doesn't stop there, because JavaScript also works really well with web graphics. And if any of you know what shaders are that execute on the GPU, we can do advanced effects and pre-process those images and then send it into the flow. So let me delete this line over here that connects this image. And before I send it in as image 2, I'm actually going to put it through a processor node that does shader rendering. So if I place that in the graph like that, lovely. I'm going to use one of our pre-made filters for now, but you could add your own code by dragging out from the shader input there and just add your own arbitrary code if you wanted to. And then I can put that back into image 2, and now you can see me, whoop, there we go, at the beach with wiggly backgrounds all happening in real time on my 6-year-old laptop. So that's Visual Blocks, and I look forward to seeing how you will use it in the future. There's so much potential here, and I'm very excited to be sharing that with you here today. All right. So we've also announced just recently the ability to share your pipelines. So using our predefined blocks, if you make a cool flow that others could maybe benefit from to start from, you can share that pipeline and allow the community to have that as a starting point to fork and start with. So here's some examples on there already. Laser hands, very cool. Low light enhancement to turn dark images into bright ones, and all this kind of fun stuff. So if you make something cool, you can submit to our GitHub, and I'm hoping this will grow as a community. And coming soon, we'll have custom nodes as well, which will allow you to define your own nodes that do anything you like. So all of the nodes in this system are custom web components. So to define a new node, you just define a new web component, register it at the Visual Block system, defining what inputs and outputs you're expecting, and boom, it'll just work with everything else automatically. So that means you could connect your system to your own APIs and services internally at your company, or maybe you want to talk to ChatGPT and bring that into the flow. You could do that. So there's no limits here in what you could make. It's just JavaScript running whatever you like. Awesome. So on to the next one then. Next up, we've also got MediaPipe, which also offer web-based solutions that are part of the web AI space here at Google. And this year, we launched MediaPipe Studio that can provide solutions such as hand gesture recognition, as you see on the slide, that run entirely in the browser. Now, you can integrate these solutions into your web apps in just a few lines of code, and many of them are customizable with their own training data, so you can alter them afterwards if you want to, and then deploy to the web. In addition, MediaPipe have some new models this year, such as the blend shape classification model, that allows you to create very realistic virtual avatars to mimic your facial expressions all in real time. So we're now living in the world where you don't need specialist hardware to do motion capture and this kind of stuff. You can use a regular webcam on a laptop in your browser and then join your next computer game with actual facial expressions if you wanted to. So some really fun stuff you could be doing with this. And I'll be doing demos of this upstairs at the Google Developers booth afterwards if you want to try it for yourself. Moving on to performance improvements, we've made significant optimizations to our WebGL backend. Now, for those of you who are new to TensorFlow.js, a backend is not server-side in our case. A backend is the environment where we execute the machine learning model. There's plain old JavaScript, there's WebGL for GPU acceleration, and there's WebAssembly for CPU acceleration. And we just launched WebGPU as well for even faster GPU acceleration. So in this case, for WebGL, we're now able to get 5.8 times the performance gain just by including the latest version of TensorFlow.js. So this is a big improvement for us this year that we announced. But how does this translate to actual model usage? So here you can see some popular models that people use over in the ML world. And these op improvements translate to about 1.59 times performance gain in these model usages. So again, just by using the latest version of TensorFlow.js. So this basically means WebML models are going to run faster than ever before, freeing up more processing power to do other things like graphics or user interface updates and anything else you want to do in your web app. Now, also this year, we had breaking news that Chrome has announced support for WebGPU in Chrome Stable. And this brings the power of 1 billion GPUs to the web, which is really, really cool, as this can enable compute-heavy applications like codecs, games, and machine learning to run much faster than ever before. And at I/O last year, we announced support for WebGPU in TensorFlow.js, and of course now you can use it without any flags, and it just works out of the box in Chrome. And of course, other browsers should follow suit in due course. But what does this mean for the WebML community? Well, this means we're now able to run larger models, like diffusion models, in the browser via TensorFlow.js at incredible speeds. And you can see here a standard 512 by 512 pixel image from this generative model can be created in under 10 seconds on a modern graphics card. By contrast, if we were to use our old WebGL backend, this would have taken 3 times longer. So really incredible things are now able to happen in the browser. And this also means we're going to continue to see larger and more complex models being pushed to the client side, that can be cached locally with IndexedDB and stuff like that, because this bad boy is 2.4 gigabytes in size. So you do want to cache these models. But we're very excited to see what models you will convert in the future too. And we're starting to see in 2023 especially a huge number of conversions happening, both from our community and other communities externally as well. Now, none of this would be possible without some amazing collaborations with Intel's web graphics team. So a big thank you to them, who've actually contributed to our open source project, which is TensorFlow.js. They actually worked on creating the web GPU implementation for the ops. And the ops are the mathematical calculations that the machine learning models need to do, basically. So without Intel, we could not have done this, and there's a big thank you to them. And you can see here, we can have 3.8 times the speed of our WebGL backend by using WebGPU. So going towards the future here, WebGPU will be the way we execute our machine learning models once it's supported in all browsers. Now, with all these great updates, even the research community are taking note. And we're now able to convert Python-based JAX models and convert them to run in the browser as well. So this ultimately means more eyes on your amazing research. If you're a researcher from the Python side, there's still a path to the web for you, and there's good reason to do that. In this demo, you can see an example where you type in a sentence, and then it matches how similar the words you're saying is to what's going on in the image. Really cool stuff. So when it says a bird sitting on the face of a cow, it shoots up to 88% because that is what is actually happening in that image. So this parity between images and natural language is becoming much more common in the browser too. And now I want to head over to our amazing community, people just like you. Some of them are complete beginners taking their first steps with web AI. Some of them are experienced experts. And I want to show you what's possible in this space by showing you some demos that they're using in their businesses today. So let's roll to the video.
Fundamentally, what we're trying to do is build tools to allow anybody to be their true self. There's a lot of people that feel uncomfortable on camera. Here's like a much more detailed side-by-side view of my face being captured alongside the face of the 3D character. And so what's happening is it's tracking individual facial blend shapes and then relaying them back into that Unreal Engine to render them.
I work as a radiologist, and the last 4 years I've been really interested in using artificial intelligence for segmentation. And this is a really nice thing with TensorFlow.js, I think, is that you can interact with the AI models. It doesn't have to do fully automatic predictions, but you can actually kind of guide the models to get the result that you want.
We're going to see an animatronic talking backpack that uses face mesh, and it was sort of a comedian in the wild experiment that respected social distancing. It does what you see. It puts all these tracking points on a face, and it can track it with and without glasses. It has an incredibly high frame rate, even in JavaScript and even in browser. So wouldn't it be great if you could use this technology to control animatronics?
So this is an example of how Cardinal Health is using RoboFlow to improve the backrooms of pharmacies. So they have a division of their company that works with pharmacists where one pharmacist can manage several locations remotely over a video stream. And so this runs in the browser on an iPad. And previously it was just a video chat between the pharmacist and the technician. And then they used RoboFlow to add on a pill counting feature that helps the pharmacists be augmented by the computer vision model so that they don't have to count from scratch. They can use the model to estimate and then adjust up and down where the model has not gotten an exact count.
The video that I'd love to show here is a video piece that I constructed, which I call Mirror Exercise. And this is an AI-generated duet with myself. So what you're seeing here is in the figure in black is my real motion capture data from a couple data taking sessions in the studio. And in blue, you see a dancing accompaniment that is generated by the model. So in each case, the model is seeing a certain segment of my movements and is creating a slight variation on it in some sense.
It's a hand tracking engine called Yoha. And so what it does is it processes the video feed of your webcam and it detects the location of your hand in this video feed. And the goal of it is that it allows you to quickly sketch something roughly similar to how you would do it on a whiteboard.
Kimo is a visual workflow engine that allows you to build very complex solutions in just minutes. And we do that through a drag and drop interface, which helps you define any kind of process without the need for coding. So this is the final version of the program. The video is a bit sped up, so things happen fast, but you can see that as water is taken out from the container, the graph reflects the changes in the level of the liquid, which is what we wanted.
We wanted to go beyond machine and even beyond the clinic. And so that's really when we decided to expand our platform into computer vision and delivering care directly into patients' homes on their own devices. We're a medical device that we can run on any device, fully web-based. And you can see these patients doing different exercises, upper body, lower body, with real-time feedback, counting their reps. We track their range of motion. We gather all that and send it back to the clinician for review to help modify their home exercise plans accordingly.
Awesome. So some really cool stuff there, and I hope that inspires you to go try some stuff out, because some of those people had done ML for the first time using our pre-made models and made some of those things. So really impressive stuff. If you do make something cool, please use the hashtag WebML on social so we can find your work and feature you at future shows just like this one. Now, I spoke about pre-trained models. There's different ways you can get into web-based machine learning, and one way is to use pre-trained models in TensorFlow.js. These are really easy to use JavaScript classes for many common tasks. And here are those tasks. We can do things like computer vision, so object classification or object detection. We've got human body understanding, pose estimation, body segmentation, hand detection, all that kind of stuff out of the box. And what about text understanding or sound recognition and many other things? And all of these can be used in just a few lines of code. So let's show you that. Earlier, you saw my demo for creating this Chrome extension that allows you to ask a question and be scrolled to the answer. How hard was that to make? Well, if I ignore the Chrome extension part, if I just focus on the machine learning, it fits on a single slide. So all you need to do is import the TensorFlow.js library at the top, and then the model of your choice, in this case, the Q&A model, which stands for question and answer. And then we define two variables. The first one is for search text. So this could be the text on the web page, basically. And then we've got the question, which could come from an input box somewhere on the web page. And we then simply call Q&A.load to load the model, download a couple of megabytes of data. And as this is going to be asynchronous, you have to use the then keyword to wait for that to finish. When it's finished downloading, it'll pass you a model object, which you can then use to call model.findAnswers. You simply pass to that the question and the search text that you wanted to use. And again, this might take a few milliseconds to execute, so use the then keyword again, and you then get an answers object returned with the strings it believes matches the answer to the question. You can use your own custom logic to then find that on the web page and scroll to it, and that's basically how I made it. So, in a few hours, you can hack together really powerful solutions that matter to you. So let's go through some of the others that are available. And remember, these can be used in the same easy way as I just showed you, but with, of course, their own functions and calls. So the first one is object recognition. This allows you to find where in the image and how many objects are in that image of a certain thing. Our Coco SSD model recognizes 90 common objects out of the box: dogs, cats, cars, tables, chairs, that kind of stuff. So you can use this to get productive pretty fast, to make things like that dog detector that I showed you at the beginning to recognize when it's near a bowl of treats and send yourself an alert, or a person detector, make your own Nest webcam or something for free. It's all possible with this. I probably shouldn't say that, but you can do it with this. And then we've also got text toxicity detection. You can send us a string, and we can tell you if it's toxic or not. Is it an identity attack? Is it an insult? Is it obscene? So now, if you've got a blog or a video platform or something that has comments, you can filter those comments before it even gets to your server into your database. And of course, you might want to do some extra checks still, but you can filter most of that nonsense out before it ever gets there. Or maybe even inform the user they're being a bit mean. So there's ways you can integrate this into your user experience. We've also got selfie depth estimation. So for a portrait image of a human, we can predict not just X, Y, but X, Y, and Z of every pixel in that image. And if you understand the 3D makeup of the human being, we can do some very fancy effects, like imagery lighting. You can cast rays around yourself in real time using WebGL. Or maybe you can do 3D photos like you've seen on Facebook and other social media sites. We've also got face mesh. That's just 3 megabytes in size and can recognize 468 facial landmarks, all in real time. You can see this running on my very old desktop at home, at 136 frames per second on an NVIDIA 1070, which is 3 generations old now. And we can even run on mobile phones at like 60+ frames per second if it's a recent mobile phone. And people are starting to embrace these models to do very powerful things. L'Oreal, who owns Modiface, are using this for augmented reality makeup try-on. The key thing to note here is that this lady is not wearing any lipstick. They're using TensorFlow.js face mesh combined with WebGL shaders in order to color in her lips very realistically based on the swatch of color she wants to try on from the comfort of her house. We've also got hand pose estimation that can track in 2D or 3D, multiple hands and multiple people. With this, you could do things like gesture recognition or maybe even sign language recognition if you combine it with some of our other models. Building on this, we've got 2D and 3D pose estimation for the full body. You can see how things like Include Health that you just saw were able to come to life using these kinds of models to do physiotherapy and that kind of stuff. It can track 33 key points on the human body and can run over 150 frames per second on an NVIDIA 1070. Building on this again, we've also got body segmentation. This allows you to separate human bodies from the scene behind it. So if you think about Google Street View, where we blur the bodies, you could use this in real time on the client machine to do that in the moment versus having to do it all on the server side. You could do some stuff like that, or whatever you want. Maybe in Google Meet, we've got a specialized version of this you can use for selfie segmentation, which is focusing on the upper body as if you're sitting down, and then you've got finer granularity around the hair and that kind of stuff too. So essentially, to wrap up here, we are at the birth of a new era that makes machine learning more accessible to everybody, including JavaScript developers, but also creatives and musicians and artists too. And this is very important because JavaScript is used by almost 70% of people in the world today. So finally getting away from Python and coming to JavaScript is a really big deal because now all of you can do some amazing things too. And there's a number of Google teams working in this space, such as Chrome, TensorFlow.js, and MediaPipe. Chrome building the web standards that enable other teams like TensorFlow.js and MediaPipe to go really fast in the web. And they all enable machine learning in the browser via JS. And that's really important because this enables some superpowers you cannot get on the server side. The first one is privacy. If you're using sensors like the webcam or the microphone, none of that audio or visual data is going to the cloud for classification. It's all happening on your device in the browser locally. The second point is it can work offline. So your customers can have a progressive web app or something like that that works offline in the middle of a field, and you can still get the job done. And the real use case for that was actually in Brazil, I think, for supermarket verification of product placements. Because often, if you've been to some big supermarkets, you never have Wi-Fi signal in there or data. So we needed to do it offline and then sync it later to make sure the products are in the right place. We've also got lower latency. We can run at hundreds of frames per second, not just 10, or whatever the cloud might offer you. So real-time applications are now able to be run in the web. And of course, cost. If you're not hiring expensive GPUs on the cloud services, as a medium-sized company, you might save tens of thousands of dollars per month if you're having to rely on those typically. So as a startup, it could be very powerful to you. And of course, the web comes with zero install. I can just send you a link, and it just works. There's no configuration of a server-side setup to get it working, and you can just refresh the web page to get the latest version. And of course, you've got the reach and scale of the web. Today, there's over 4 billion browser-enabled devices out there. So those are now your target audience that you can deploy to in a frictionless way. And this is only going to grow in the future too. So if you've been inspired by anything I said today, and you want to go from zero to hero, I've got a free course on Google developers that you can just take and magically become an expert in WebML. You don't need to have any background in machine learning, just need to know JavaScript. I'll teach you all the machine learning parts. I've kept it on purpose, not too mathematical. You just need to know how to add, divide, subtract, that kind of stuff. That's all you need to know. And I guarantee you'll be able to understand how a neural network works by the end of that course. You'll be able to use our pre-made models. You'll be able to make your own models from scratch. You can convert models from Python to run in the browser, and much, much more. So go to goo.gle/learn-webml to take that course. And with that, thank you very much. I believe we've got 5 minutes for questions, so I'll take those if you've got any. And if not, I'm on LinkedIn and Twitter as well. Thank you very much.